Anyway, Tom got his PhD from Durham in 1989, and then he held faculty positions at various places, including Berkeley, ESO, Tel Aviv, and then since 2010, he has been a faculty member at the University of Basque Country, and he has been involved in several large international programs, particularly the construction of the advanced camera for surveys on board of Hubble, which is still a very popular camera, and also he is deeply involved in CLASH, another HST program, so as KT. He has very rich experience in observational programs, and he's a leader in lensing. So he will exploit lensing in probing the population of black holes and stellar population at high speed. So that's welcome, Tom, again.
Well, thank you, Yunting. You'll see that this slide is very familiar from your talk last week about the Hubble constant paper that you reviewed. I thought an excellent choice of paper there that you reviewed. And I'll show that much of what I'm going to talk about today, in fact, derives from the discovery of this cluster as a lens in collaboration with my colleagues there in Spain, Chema, we've got Jose Maria Diego, we call him Chema, George Smoot in Paris, Pat Kelly in Minnesota. Nick Kaiser also sadly died a month ago, as you may know. Very tragic loss, especially as many of us admire him so much. And then my former student Adi Zitrin in Israel, who has also visited here on a number of occasions. So, with Adi, we first we noticed that this lensing cluster, at first glance, we've been in the archives for a number of years before we got around to looking at all these different max clusters. And if you look at that image on the left, you would think, oh, there's this foreground group of spiral galaxies in front of this cluster, right? And no one realized, actually, they're lensed images. How can that be? It turns out, from our modeling, that we can understand that these clusters recently merged, and the mass distribution in the center happens to be at the moment rather flat. So and the density of dark matter is so high that it acts as what you might call a critically convergent lens. Convergent lens is just the name for a normal magnifying glass that will just magnify things without changing their shape. And this is what this cluster does essentially. The source, you can see, looks just like the lensed images of it, more distorted in the very middle, but these 5 images of this thing are essentially larger versions, and so it's acting exactly like an optical lens, a magnifying glass. So with a critical density, that's the density of dark matter required to achieve multiple lensing. So that's the sort of Einstein ring that we were able to model, defined from initial images back in 2015 with Adi, and subsequently with Keiichi we've done the weak lensing, and this became a cluster that was part of the Hubble frontier field. And here's the frontier field data. You see tremendous depth there, and we found this lens supernova. We also claim to find an offset massive black hole near the center here. I won't go into that today, but just to show you what you can do with lensing data, particularly since multiple images lie so close to the center of the BCG that you can detect this black hole. Then we monitored this cluster. We're still monitoring it. Now with JWST, we expect to get more data very shortly. And we see that the supernova went off, and that became this new paper that will be constrained H0 that Yen Ting reviewed so thoroughly, I thought, the other day. So we won't be mentioning too much about that. But what appeared here was an unusual transient event. So we look at these images, we saw this, well, the team monitoring this, I was included, but I hadn't really taken much interest in it up to this point until they asked me, what do you think this might be? Well, they asked, we got a request for ideas, and my idea was immediately rejected by most of the team members. And that was simply that this thing was right on the Einstein ring and is a lensed star. I even estimated what kind of star it must be. It must be a B supergiant to be that bright at that distance, and in the spiral arm of this lensed object. You see, it's right here. To me, it seemed, cannot be a coincidence that it lies so close to of course our predictions are not perfect, but it's essentially within a few tenths of an arc second of where the Einstein ring must be. And so, in principle, of course, lensing can highly magnify. The limit comes due to the finite size of the source, which for a star is a factor of a few thousand. And I'll show you how that works in a minute. So yes, it's quite, in my opinion, it was clear. And eventually became everybody's opinion. So we, together with Nick Kaiser, we modelled it, became very convinced that this, in particular because of the way it showed this caustic crossing behaviour. So it brightened up, then it dipped in brightness for a while. You'll see about 20 days there. And then for a period of just a couple of days, we caught it as it crossed the caustic. That's quite crucial, and that tells you the size of this object, which turns out to be a star. Now, the way we should think about this is that the background source, the observer, the lens, of course, are all in relative motion. A large part of that relative motion presumably is from the cluster, since it's more massive, have a larger peculiar velocity. And because of that relative motion, in principle, an object may change in brightness, especially if it lies very close to a critical curve. In other words, on a caustic, near a caustic, in the source plane. Then the caustic actually sweeps past the observer on Earth, and you see, noticeable change in brightness that in a characteristic way. Now this is the simplest model of that, where you can see here there's a little inset which is the source plane, and here's a small disk. Notice it's finite in size, near a caustic, and then what you see in the image plane, some way away on the Einstein ring, will be two images that will approach each other depending which way the star is crossing the core stick, they might diverge. And those two stars, those two images, we cannot resolve them. So what you would see is a net change in brightness. This is a milliarc second scale, so not resolvable by Hubble, but the brightness of the pair you would notice changing. So here's how it works. So as the star crosses the core stick here, the images become maximally magnified, and then during the transit, the magnification is approximately constant. Maybe I can just sort of pause it as it crosses. You see here. So that will stay about this brightness while that star crosses. And you can understand that, you know, if you zoomed in on there, you have to integrate over the surface of the source, calculate the mean magnification, which is not going to depend much as the core stick is passing over. The rest of the magnification on average will be about the same. So it stays like that, and then it disappears as it's now on the other side of the core stick and doesn't form multiple images. So that explains this behavior here and the general rise. You can also notice that it fluctuated here, and so this is a sign of micro-lensing, and this shouldn't be too surprising that micro-lensing is happening here, because there are a lot of stars in the lens. So this can then become a star in the lens, adding to or subtracting from the magnification of the source, which is also a star. So you get fluctuations imprinted depending on the density of stars. So these stars will be in the envelope of the brightest cluster galaxy that you see there. Maybe you can see it better here. Yeah. So you see this. That extends, and you can calculate based on the surface brightness what you should expect in terms of the rate of micro-lensing by normal stars. And so it actually looks a bit more like this simulation here, where you'll see now two images appearing, but with extra perturbations from micro-lensing stars. There's one. And they appear again. Yeah, okay, there's an image appeared. Let me see, the second one appeared here. Situation gets a bit more complicated. Right? So imagine that you don't resolve this, but you're measuring the brightness. You'll see this star come and go as a function of time, or fluctuate as a function of time. So that is, well, maybe this is better. Let me try that. Not sure that's going to work, but right. Actually, it's more like this. So there's the two images that would add up to something that we detect, and then another pair appears. So it got brighter at that moment. Still quite bright, a lot of things going on, and then totally disappeared. There could be a bit more like what's happening. Now, if the number density of lenses is really large, if there's a lot of micro-lensing, so for example, if you made all the dark matter out of, say, stellar mass objects, suppose it was all baryonic, well, it would be dark, so it can't be baryonic, but it could be like black holes, for example, stellar black holes. Then you see continuously images appearing and disappearing in this region. You see it's a very small region, 1/10 of a milliarc second, and all the while you'll be detecting light, and it'll vary over time. Hopefully that's clear, right? The thing to remember is all this light is seen basically in one Hubble pixel. And it should vary with time in a way. Now, what we don't see is this behavior. This would be too frequent, and therefore it limits the proportion of the lensing matter in compact objects. For example, primordial black holes. So that's the first thing we did, was we created simulations with large levels of microlensing to try and determine the upper limit that we could accept on any primordial black hole interpretation of the dark matter. Because as I say, as you increase the proportion of microlensing, the proportion of dark matter in black holes, then the fluctuations in the light curve become much more frequent. And what we observed over time was that, as I showed before, it did vary a bit, then it disappeared, and then it came back again. 2 years later, we saw an image of it over here. It might not be the same thing, it could be an image of another star. And then we saw later some evidence that there was another image appeared offset like that. So the behavior is a bit more complicated than we're modeling, in fact, but it isn't showing this rapid variation that, and so we limit the mass of microlenses to about less than 1% of the total column of dark matter. And of course, we know that it's on the Einstein ring. We know how much dark matter there has to be in that lens at that position, and so we can say that it's a very small fraction that's allowed. Here's another way of seeing that. So now you could take a limit where if microlensing was so enormous, then you may not measure these tiny fluctuations. But there are caustic crossings during this time, and so you would see sharp peaks. So the statistics of the behavior really help discriminate between smoothish and primordial black hole, or any kind of compact object that might comprise all of the dark matter. So we put limits with this data in this range, basically.
So the time scale is years.
Yeah. You have to measure it over years. Yeah.
Measured over tens of years.
Yeah. So far, we've monitored it for about 10 years. Yeah. So, but you see, if there was very rapid fluctuations in smaller timescales, that would tell you that you had look at that. So you had a large column of. That's what we don't see. Okay. Anyway, that turned out that this. We started monitoring other clusters, and we saw that other such stars appeared. There were two in this arc here. That they were a little bit puzzling because they're not close really to the middle of the arc. If you sort of naively thought the critical curve was passing through the middle, but anyway, in detail, lensing of this arc is complicated, and that's caused by perturbations from neighbouring galaxies. And in fact, our good friend Oguri-san, Masamune, of course visited here many times, he was able to construct a model where the critical curves went directly through those two positions. So this is a level of modelling that's just perfect. In other words, if you wish, you can do it. A sufficient number of free parameters, and it's plausible. And perturbations by these galaxies can give you that, because you need the magnification to be very high. So the critical curve somehow got to do that, because these are stars. We can see, and we have another case here inside this Jupiter-looking object. There's another varying point source. This is the behavior as well. You see that we track them for a while and just disappear. Very characteristic of caustic crossing. And so we keep looking for these lens stars, Some of them are brighter than others. We even gave a name to this one. And where is it? It's here. Yeah. See that thing is incredibly bright, and it doesn't appear in the counter images. So in all these modelling that we've done, this is careful work by our close collaborator Keiichi and myself, I mentioned before, Chema, and he demonstrated that multiple images of this star should be seen, and yet they're not, and so it presumably is changing because the time delay for arrival of these other images is varying. Then we thought, well, let's systematically look for these things, and we got a large Hubble program going in the last 3 years with Pat Kelly, who's done with his student postdoc Wenli Chen, some fantastic work on systematics here. You know, the important point he realizes that you should always reobserve at the same rotation angle because of the PSF complications. That allows you to subtract the PSF so much more cleanly that then you can notice these small scale variations. So in this giant arc there of AWOL 370, we noticed several cases here. Look, you see, these are difference images, and so you know that means there's something varied here at this point. Brighter in the earlier image, this one's brighter in the later image. Another two here, another two here, and the critical curve is waving through here in some way. Now it turns out that what we started to notice is that some of these stars are not on the critical curves; they're slightly off, and that's a very interesting clue that I'm going to just remind you of here. And some of them don't vary at all. This is another really strange problem. For example, this one. We've got JWST images now. You see this arc here. We re-imaged it a few times with Hubble, and there's a point source in the middle that we now have a very good spectrum of. This thing here, it's a bit hard to see somehow on this image, but we just sent this to the journals. And you can see that with the spectrum clearly shows a Balmer break for this point source at a redshift of 4.76, and it doesn't vary despite being very close to the critical curve and without the presence of counter image. So if you see a point source close to a critical curve, you don't see a counter image, you think, oh, there must be varying. But since we've got images over time, we don't see any variation. So it might be that this kind of object is, in fact, a globular cluster, a young globular cluster. In which case it would have strong Balmer lines, and we need maybe a better spectrum to discriminate between a single star and a Balmer line. And so we're finding a few of these things as well now. This is another example, in my opinion, this could well be a star cluster, compact star cluster. The critical curve definitely passes right through it, basically. You can tell by looking at the counter images of this thing. But it didn't vary with time, despite the depth of the Hubble and then re-imaging again with JWST. But there's only one image, you see, so it has to be right on the critical curve, and that's probably another case of a dense star cluster. Although we didn't kind of sell it like that. It's supposed to be the most distant star. Here's one that does vary a bit, but only in one passband, in the blue. We found another one at redshift 2.6. This shows you quite nicely, you see that if you notice this pair here, these two counter images, these two are counter images. These will just be H2 regions. The critical curve, therefore, must pass through the middle of these two pairs, right? So somewhere on this line here. And there's this source appearing very, very close, but not quite on that line. So we keep trying to explain these with a small perturber near the critical curve to kind of give us that offset without creating a counter image. It gets a little bit contrived. I know quite a few cases where we want a mass of around 10 to the 6 solar masses, this one, close to this source. And so you start to wonder how plausible is it that all of these things would have such a dark object of that mass, typically 10 to the 5, 10 to the 6 solar masses. Here's another one we just found. It's just off from where there's a range of possibilities where the critical curves are, but it's definitely not on any of those, these different models. There it is here. So this is certainly offset again from where you would expect it to be if it's a highly magnified star. This one is varying, so we know it's a star and not a star cluster. So we keep in mind, and I come back to this, that in the case of this wave dark matter, we have a long tail of high magnifications, and we can produce much larger numbers of stars that are detectable thanks to this long tail, and they wouldn't be near, typically, where you predict a smooth critical curve to lie like that. The corrugations do this. And so we have made some claims about that just a few months ago. Now, when it comes to lensed, so what I basically hopefully convinced you of is that compact objects, stars or star clusters, can be very highly magnified, thousands of times, and the limit is set by the size of the object as it passes over the caustic, a few thousand times. Okay? And this is pretty common. Every cluster that we look at, we find these things. We find several per cluster. So we have these systematic programs that keep finding more. Hopefully we'll figure out what it all means. But nevertheless, no shortage of these lens stars, and the statistics will become clear. Now, what about these binary black holes? This is, in my opinion, very related problem, because as we know, these are surprisingly massive binary black holes, and they, by the way, this is cagey to appreciate. This cat is detecting everything with his eyes, electromagnetic waves. He's presumably maybe feeling the radio waves. And of course he'll have to compensate for any gravitational perturbations caused by passing gravitational waves. So I don't know if it's really that setting, but you know what. The sensitivity, wonderfully, of these things is picking out these frequent cases, mainly binary black holes, as you know. There are 2 binary neutron stars, one of which was detected in the optical, confirmed, and there are some cases of neutron star black hole binaries. They're really interesting. They can be used for H0, and I'm going to end with that in a few minutes. Well, let's see. And of course, now we just heard about nanograv and binary supermassive black hole possible detections. So gravitational waves is really opening up. And you can see, this is what I call a graveyard, right? Graveyard plot. I think you can tell what's going on just by looking at this plot. I'm going to reorder it in a minute. But fortunately, it's on a log scale. And so you can easily notice that, you know, let's say you take, let's take this one. You see there are these two masses became this one. That's what these waveforms tell you. You can measure the mass ratio, and you can see that what the final mass was, and you get a pretty good idea of the mass ratio. You see they're all pretty similar, right now, but there's a kind of a row here. They plotted them like that just for artistic effect, I suppose, right? These are the most massive ones. The size of these circle discs is proportional to mass, presumably, on this log scale, right? From neutron stars here up to the most massive claims of over 100 solar masses. Right? That's crazy for a black hole, a stellar black hole. So now, if you sort of think about them, you can also wonder, well, is this a second row here, right? You see, these all got the same. The mass ratio is pretty much the same. It's you know, there's about not exactly 2, but about 40%, something like that, right? Let's say almost 2-to-1 mass ratio for all of these things, and there appears to be. So anyway, you know, for those not familiar with LIGO, what they determine from this chirp is this kind of sound, right? That's what a chirp is. Chirp mass, just rising in frequency, like a bird, you know, chirping, sort of. We got that right? Anyway, you can see it here, right? In frequency over time, the event rises in frequency and then quickly dies as the in spiral ends and the final black hole is created and settles down, and there's no more gravitational wave emission. And this change, this rise in frequency here, can be fitted and provides a mass. That's the mass of the combination of the two in-spiraling black holes. Right, M1 and M2, that's M1 and M2 here. So you can maybe notice that if you rescaled, well look, there's a redshift to worry about. The higher the redshift of this binary, the lower the frequency will be, and that gives rise to actually a larger chirp mass. The more massive the pair, the lower is the final is this frequency generally. But if you need to know the redshift independently of the masses if you're going to interpret the chirp mass, because it combines the redshift and the mass. This combination of the masses, it's a binary mass, reduced mass almost. So this product is what you know. Now what they do, I'm going to talk about lensing, and what lensing doesn't do is change this frequency. These observed frequencies are not changed, but the amplitude, the strain is magnified. So you think the whole thing is closer because it's stronger. So to get the redshift, you look at the strength of the signal, and then you fit for that, and you use that to give you an independent distance. Convert that to redshift, and then you can solve for these masses. And in fact, you can measure the mass ratio if you have a detailed enough strain spectrum. The exact details of this behavior tell you the mass ratio. And so you go, in principle you can do this, but it does rely on interpreting the strain. Now, for lens sources, you will underestimate the distance. You'll think they're nearer than they really are because the strain got magnified. And that's the key thing here that we realized. Now let me mention, before I start trying to convince you that all of these, basically 80% of LIGO sources, in my opinion, are highly magnified at a large redshift, and not what they're thought to be. Let me mention that as you probably know, right, the sub-millimeter sky, the brightest sources on the sky, like these objects here, is a big patch of sky mapped by the Herschel satellite. Many of these sources turn out to be gravitationally lensed, including this famous one that was well studied here by Sherry and others that we talked about last time. That thing is very highly magnified, and so what that says is that the brightest sources on the sky, that's these, measured by Herschel in this long wavelength range, are all turned out to be lenses. It's a very efficient way of finding lenses. You can measure the Einstein rings. When you found them, they zoom in and they see rings in every case. They're all so magnified that they're right on the critical curve, and then they fit this model to the data. There's a whole industry there. They've found hundreds of these things now. And so, as I say, this one with ALMA, it's an incredible lens with all kind of funny wiggles. We've been working last week with Suteng. I have to bring you up to date on that. It's very interesting. Yeah, very interesting. Yeah. So the point is, you've got to worry. So that if you are surveying the whole sky, if you're open to detecting the whole sky, like LIGO, the strongest events could be lensed. It is not ridiculous to think. I mean, here it is the case that the brightest galaxies known, these sub-millimeter galaxies, bolometrically the brightest, are all lensed. I'm not saying the most luminous, I'm saying just the brightest. It's remarkable. And the reason that they stand out like that is because the number counts of fainter sources quickly die off at bright fluxes. There are not that many. So these lens sources all kind of stick out. They're all brightened up above that. And that's how you can easily detect them. You just take the brightest one. So with LIGO, what we noticed is in the first 6 events is that 4 of them have these large chirp masses and 2 of them don't. Right? So we would bravely claim that these 2 are just normal stellar mass black holes. Nothing surprising about them. Those are known in our galaxy. All the stellar mass black holes lie in the range of 7 to 12 solar masses. So here's, and if you were to take the population of such galaxies as your prior, you could detect them with LIGO out to around about a redshift of 0.2ish. And there will be some trend there because the redshift slightly expanding this scale by 20%. Right? So this is the sort of locus where you would expect to find black holes that are stellar, like in our galaxy, that are known. But then we say, well, okay, let's input that and ask, given what we know about lensing, especially from the optical depth that you estimate here, what the probability of lensing that you see here, 1 in so 10,000 lines of sight. It's highly magnified. You can put that's known. You put in a mass distribution as just Gaussian, just for simplicity, and then you can ask, well, how detectable would they be with LIGO? And you must correct the distances for the square root of the magnification. That's what happens to the strain. And you would expect all this stuff here. This is the magnification. So the most highly magnified cases on the Einstein rings, presumably of distant galaxies, just like those ones in Herschel, maybe the same galaxies as a matter of fact. If black hole binaries form in those galaxies, highly magnified, they will be found at these kind of chirp masses. You will think that they're very massive, and you will assign them very low redshifts, but actually they're very high redshift, and their masses are no different from these. And this is the trend of magnification. Lower magnification, lower chirp mass, as you'd expect. They eventually fall back on this line. So these 4 points fitted our approximate calculation, and these two, we say, are unlensed, these 4 lensed. So that's a sort of a ratio of 2 to 1. And you see what? So those that you think are highly magnified, very small distances because it's so bright, in fact lie at high redshift 2 to 3. And these are all the lensed events that you could dominate this plot, depending on how many such events there are in the early universe. Well, high redshift. So we can calculate the evolution. How many do you need relative to today? And it's 2 orders of magnitude higher at redshifts of 2 than today, in terms of a ratio of this 2 to 1, in terms of high redshift to unlensed at low redshift. Okay. Now the data subsequently has become fantastic, and if we look at the histogram now of the chirp masses, you see is pretty convincingly bimodal. This peak here, centered on about 10 solar masses, would be the unlensed cases. They're over here. This is the data. They're over here, and on this plot, mass 1, mass 2, the final mass, and then if you take that as your input, you predict this distribution here at high redshift, just from lensing. And you see this sort of should rise up there, peaking at about 30 solar masses, and then drop off like that. And there's not much room for altering that prediction, because what matters only really is the volume available. The distribution of magnifications is just fixed by this caustic behavior that I showed you before. It's well-defined and independent of the mass of the lens and so on. It has the same form. So that gives you this spread here, and it really does fit this data. So all of these, we reckon, are all in. So now the ratio looks a bit more like 4 to 1. So that there's about 80% of all events. You can even see a distinct jump, I would claim. When we make models of that, as these here, we see that distinct jump. And furthermore, if you divide through by the total mass, you see you get parallel lines. They all pretty much got the same mass ratio, these black hole binaries. That must be a really clear clue. That they don't tend to have the same mass. They tend to be different, but by a fixed ratio, this 40% that I mentioned. If you just were to select at random, you see you get this scrappy prediction for M1, M2, like that. Whereas if you fix that ratio within a narrow range, you can reproduce the data. So this is a sort of simulation. I mean, it's a very basic calculation that shows you that you can understand that these things are all the same. The low redshift, that's redshift less than 0.2, is unlensed one, and all of this stuff here, all these high redshift, all the same. They all have basically the same mass ratio as black hole binaries, and the only difference is that these are all lensed and these are not. So it's become very, very clear. Another thing you can do is you can look at the waveforms of events that are compatible with being at the same location to see if you can see repeating events. We claim in some cases you can. I mean, these waveforms are a bit noisy, but there are pairs like that, these two events here, they're here on this plot. So with Virgo, they can, when you get 3 detections, you can kind of narrow, zoom in on, narrow the range of where they are in the sky. And you can see that there are, if you go down this list, you can find cases that look, events that look extremely similar. And that means that they have the same waveform. So it's not hard to convince yourself. And in fact, of all events that look similar, their time scale, the time separation between them, is of order of 30 days or less. Very similar to the time delays for lensed quasar images. So you can't tell at the moment with LIGO, if you're really seeing a repeat event. Maybe when CAGRA comes online, the triangulation will be so good, and you can be pretty confident. But you can ask, well, is the time delays consistent with being lensed by galaxies? Galaxies being the most common kind of lens, as Herschel has revealed. And indeed, it seems like the time delay distribution is not consistent with that known for lensed quasars. Okay. So we've been making this case steadily, and we've come to the conclusion that these things are pretty uniform. Okay. And there are some outliers, you can see, and some of these outliers, these two here, these are neutron star black hole binaries. So these ones, the large mass ratio, are now you can tell are neutron star black hole binaries, and we reckon there are lensed examples of those as well. Okay. So we also made that point, and a few other things, right? So that at the moment, I would say the party line amongst the LIGO, Virgo, the team, is that lensing is rare, and therefore they look forward to finding lensing one day. Right? This is what they tell us, especially our referees. It's been a painful process where they keep saying that. But of course, the point is that magnification makes it very possible that the ones you do see are the ones that are most magnified. And in fact, the bimodality here that's now observed is really easily understood in the lensing context. Whereas if you believe these masses are intrinsic, as the LIGO people do, they have now to come up with multimodal. So their latest models have multimodes. That's the latest prior. They have prior multimodes.
So in your lens interpretation, what typical the redshift of these binaries?
Right, they will be like that. Yeah. Above redshift 1, and the tail out to redshift of 4. That's the prediction.
And is there any, implication for the major rate of the black hole?
It is high, yeah, higher than today, you know, but it crucially it's below the rates that you would infer from supernovae. So the core collapse supernovae, the formation of black holes, let's say high Z stellar mass black holes, is lower than these numbers here. So you know you wouldn't want to violate that, presumably, unless you thought that some black holes form without forming supernovae. But there's no physical problem with this rate, right? So it's, we would say, about 1,000 per giga-year, per 1,000 per year, sorry, per gigaparsec cubed, cubic gigaparsec. So it's a very small rate. It's like 1 per galaxy per, how much was it? Several years anyway. I have to check that.
And any implication for the population of lenses for these?
No, I mean, all you need is, well, the optical depth for lensing we know, so we're not changing that. We input that. That gives you, you know, a fraction of the sky that's highly magnified as a function of magnification, and that's fixed. So you may say, well, the rates are a bit high, and if you did, then you could appeal to wave dark matter. You see, you could have more highly magnified point sources. So we're actually quantifying that now. I think it is a relevant calculation, especially because we see for those lens stars, the same redshifts, that there is this high rate. So you know, you could probably boost that by a factor of a few, you know, by wave dark matter. But that's not crucial to this argument. The crucial point here is that you can just tell that it's all one population, and this step here from lower mass to higher mass. Now this is a log scale, so you can just multiply up, just shift linearly upwards these, and it'll give you these. So we do think it's very simple, very easy to interpret that in the lensing context. So this is what's funny. This is just that same plot that I showed you initially, but it's ranked by chirp mass. This is artistic, and this is scientific, if you like. But it does reveal this feature, this kind of jump, and we think we understand what that. It's just a transition between low redshift, less than 0.2, and redshifts above 1, where they're all lensed. See? A jump in mass. Okay. So, how are we doing for time? Oh, nearly finishing, right. There's one thing we can do, we've realized, with the neutron star black hole binaries that could be very interesting for H0. So, thinking about these distances and so on. You see, if we rely on, say, these two events here, and all this range we reckon is unlensed. Right, so these would be unlensed neutron star black hole binaries, the mass ratio. So these are known cases, have been identified by the LIGO team. And if you use the fact that neutron stars have a very narrow range intrinsically of mass, then you can take those waveforms and determine the distance from knowing this, that one of the components has an absolute mass of about 1.4 solar masses. So these two that have been claimed, and maybe there's one that's they sometimes claim and they sometimes don't, depending on who's catalogued. You would see that you can use those waveforms and that absolute mass scale to give you a determination of H0. You need a few more of these events, but presumably there will be plenty more soon. So we reckon that this is a method that does not rely on an independent redshift. Okay? So binary neutron stars, you can only see them very locally, there's one case where an H0 determination has been made thanks to the optical gamma ray emission, where they can determine the redshift of the host. Here, by simply making use of the narrow intrinsic mass range from neutron stars, you can make estimates over the redshift range where you can detect these neutron star black hole binaries, which is much further than the binary neutron stars. So you've got that extra volume and redshift range where you can determine H0. So we just have this, we just sent this off last week, and we hope that will provide, you know, an independent, it looks like completely independent way of measuring H0 that doesn't rely on the difficulty of finding an optical counterpart, and that will add to this method that was so well reviewed there by Yenting last week. So I was going to say that we have these two approaches now that we're pursuing in relation to Hubble constant from these multiple supernovae and these lens neutron star binaries. As I say, keep in mind that all the optical depth calculations, the locations of these compact sources could be subject to this wave dark matter perturbations that I was emphasizing in my last talk. This great idea that's based in Taiwan, thanks to Zihong and Justin and his team. And they've given us a new way to think about dark matter with very interesting implications for lensing. That we maybe the ultimate use of all of these compact sources, stars, gravitational waves, will be in determining the nature of dark matter, as a matter of fact. So that's my conclusions. I'm a very big fan of what used to be called fuzzy dark matter. You compare fuzzy dark matter, which would you prefer? Or this kind of cold dark matter? So if I was to summarize, you know, this was meant to be the conclusions of my talk last time. Let me just say, you know, there's an abundance of lens stars, and there's a shortage of lens low luminosity galaxies at high redshift. Right? So it sounds like a bit of a contradiction. How can you have few galaxies but more stars? Right? Because stars are in galaxies. They don't mean it that way. I mean, they're all lensed, and the biases that lensing causes can pick out these stars, especially if the dark matter is wave-like, and then there would be late galaxy formation and a shortage of galaxies. And this together can give you a constraint on the boson mass. Direct measurements of substructure and with implications for gravitational waves. So let's leave it at that. I think that's it. Thank you.
Thank you very much.
I have a question about some different related to the wave diagram, but slightly different point of view.
Right.
So, in the context of this cluster lensing, when you model the contribution from wave dark matter, like this wave structures,
Right.
I wonder if what would be the effect of the tidal force acting on the wave dark matter subhalos compared to CDM?
Yeah, there's a big difference. Yeah.
So how you can model, because you have to take into account this substructure.
Well, you see, our substructure are the waves, right? The waves themselves respond to any evolution of the potential. So they're always there. That substructure, you can't remove it. You can't erase it. Whereas for CDM, with all those particles, if you put a subhalo in orbit around a more massive one, then indeed you're going to erase it tidally, and you won't see anything like the level of substructure that you might naively expect from the input power spectrum, especially in clusters. But with wave dark matter, you see it the same. In fact, it's worse because the higher momentum of the cluster means that the de Broglie scale is smaller, 1 over the momentum. And so smaller and more massive. And that's the calculation that we've made now. We figured out how to do that without making simulations, because the simulations are so tough. But this is essentially, it's a Gaussian random field projection of all the fluctuations at the Einstein radius approximately.
So it is specifically for the substructure in the cluster?
This is meant to be a cluster, yeah, cluster mass. You get these tremendous corrugations. You get individual islands of high magnification around positive peaks outside the critical curve. On the inside, the magnifications appear where the density is reduced by the waves cancel. So that's very interesting statistic.
This kind of picture will kind of be modeling the substructure consistent with like a how to say, detailed modeling for the lens like Masamune's models can predict this picture.
These will be very fine scale features on those. His perturbations are larger wavelength than that, if you like. So, yeah, what you want to do then, if you wanted to sort of improve it, you would put these fine wiggles on there as well, right? And then you might not need these excursions. Right? That's what we reckon. In some cases, like this one, where is it going? With JWST, we're now finding like this offset arc that I mentioned. Where is it? This one here. You could get wiggles that cause excursions out to about a few tenths of an arc second, and that could be responsible then for giving you high magnification much further away from the critical curve than you imagine. And so then these models would have to have this. So you'd really never be able to individually model that, right? Because you need to make so many realizations before you hit the right one, right? It's like a monkey trying to write Shakespeare or something. It would be an accident. But statistically, you can ask, what's the size and distribution of the offsets and the relative magnifications. And that's what we tried to do in this paper that I just mentioned here, where we recently, tried to quantify that behavior here. So we think we can account for, in a particular lens, a radio lens, where the details are so good, we can account for this the behavior of that lens. So that's yeah.
So I'm curious, how do you quantify the size of this lens objects? I mean, whether it's a single star or a cluster. Can you explain?
Yeah, in the case of a single star, you should only take seriously those that change in brightness. And then if you see that the brightness saturates, then that gives you the scale. It's a little bit hard to imagine, but say you've got your staff, and you zoom in, and there's your critical curve. The magnification, is sort of rising up, right? Let's say ideally it would go to infinity and come back down again. But as this star approaches, as it starts to cross the critical curve, you see you've got to do an integral of this function over this surface. So there's only a very thin slice that's super high magnified and the rest are lower, right? So as long as the star is crossing here, the magnification will basically flatten off and then disappear. And that gives you the size of the source. But it's the size of the star divided by the time scale is going to that divided by the relative velocity lens and stuff. So if you put in a reasonable number here, you know, like say, I don't know, 500 kilometers per second, and this lasts, say, a few days, divide by 1 plus z, that will give you the size of the star.
So, for the case of Arendelle, I think it's unclear whether it's a binary star.
Well, yeah, that doesn't vary, you see. I've been telling them that. I mean, you still want to know the story. I kind of complain about it. I say, well, it doesn't vary, you know. So in the early days, we were having a big debate about that. And finally, I got the draft back, and I realized that my name's on the end. So I thought, I better not complain about that anymore. You know, anyway, yeah. So I you know, it will all become much clearer. I mean, in principle, that could be right, but you've got to come up with a very good reason why it doesn't vary in time. And what Chema is saying, in a sort of perhaps not entirely convincing way to me, is that, you know, if you had a lot of micro lenses, you might be in this regime. But then why doesn't that then apply to all of these cases? See, it's just, the logic's not there. You have to come up with it. So especially at this redshift, you know, the magnification required for a star, a redshift 6.2, is so much greater than, you know, the distance, the luminosity distance, compared with these lower redshift lenses like redshift 1 and 2, where we do know we see varying stars. These high redshift cases, they don't seem to vary, firstly, and the luminosity distance is much more. You've got to square that, and the magnification's got to overcome that. So then you need an incredibly luminous star, and then they start talking about population 3. I don't know. I honestly think this is not yet at all clear. Some things are clearer than others, and to some of us more than others.
I thought they are using spectroscopy. I mean, they are doing spectroscopy on this.
Yeah. I'm actually not quite sure exactly what's going on with that. I should pay more attention. We have these team meetings, but you know, if it looks like this one, I think it does, in terms of the spectroscopy, it'll be hard to distinguish a bright, you know, B star giant from a kind of quenched stellar population that's been, you know, post-starburst. This is what you would call post-starburst. It's got strong Barnum eyes that's dominated by A stars. That can actually look surprisingly similar to an individual B star, presumably because of the way the low mass stars bring this up. I don't know. So, good spectroscopy is required, but it should be feasible to distinguish.